Welcome to this Synology Spot webinar on Optimising Storage Performance with SSD. My name is Ryan Rassi and I'm a Business Development Analyst here at Synology UK. So here's our agenda. First, we're going to go over SSD caching and how this can benefit you and when is the right time and type of workload to consider this. And then I'm going to move on to all-flash arrays and how this might benefit over an SSD cache in your deployment. Then I'm going to go over some new products that have been added to the Synology range and how these can benefit you, and also why we've decided to enter this market. Lastly, I'm going to go over the technology, so I'm going to talk about the choices, benefits, and drawbacks. So, first of all, it's SSD caching. So I'm going to talk about if it's right for you and how it can impact your workloads and really benefit you. So, here's SSD cache, and it can add loads of improvements. The objective of an SSD cache is to increase the performance of random access to a small portion of frequently accessed data in the storage space. Now you can implement two types of SSD cache, and I'll demonstrate that shortly. There's a read-only cache and a read-write cache. So in general, in business storage, you'll find what we call hot data, and this is accessed every day, so it's things such as vital documents, and it's very frequently accessed documents. And then archive data is what we call as cold data. So it's things such as historical records. And ideally what you want is for the hot data to be in very fast storage, such as SSDs, and then the cold data to reduce costs on a hard drive disk. So you can see here we have the hot data and we want the cache to be about the same size. So here's how we use the SSD cache advisor. So here's our storage pool in the storage manager in the DSM, and then we click SSD cache on the left. We have the SSD cache advisor here. Now this can tell us how much space we'd need for SSD cache, and that tells you why you need to create it. So here, it's going to take a few minutes, but once it's done, it'll give you a recommended size right here. Now, how do we implement the SSD cache? Well, first we're going to go back to the storage manager in the DSM. And here's our storage pool again. And then we're going to click on SSD cache again on the left, but this time we're going to click on create. So we're going to create a read-write cache here. And then we're going to select our drives that we want to utilize for this. We can choose our RAID type here. And then this is to modify the allocated size. So we're going to leave it as it is. And then we're just going to confirm that the data on the SSDs will be removed to create this cache. So now I'll load, and it's just applying these settings. And here you go, it's now mounting. So from this point on, read-write cache is when you're accessing and manipulating the data and committing this back to the storage. So maybe a HR record. And a read-only cache is where you are accessing data but not changing this in any way. So for example, a manual. So now we can see our SSD cache, and here you can see the use capacity of it, the unused and total capacity we have for it. So this basically helps you monitor the SSD cache. So now I'm going to talk about how to prolong the lifespan of your cache. So the SSD cache configuration allows you to skip sequential I/O. So since sequential I/O doesn't benefit from SSD caching, this means that the sequential reads and writes will be faster as less data will transmit via the SSDs. So a great example of this is if you're streaming a film, as it means it can skip the SSD cache and read the film directly from the storage drives. So this in turn increases the lifespan of the SSD in the cache. So what sort of performance boost can an SSD cache offer? Well, we tested one of our 12-bay Plus series units, populated with 10 Western Digital Red Pro disks, and this is in a RAID 5 configuration. Then we used 2 bays to host two 240GB SATA Intel disks to act as an SSD cache. We set the IO meter test settings to simulate one worker, and then we let this run for about 3 minutes. We then ramped this up for about 30 seconds before we started the test, and then we used 20 gigs of data with an SSD cache size of between 10 and 20 gigabytes. Now the workload, or payload size itself, was 4 kilobits. So here are results. And they show how an SSD cache only half the size of the hot data set can boost performance by up to 2.7 times. Now, interestingly, when writes are involved, either 100% or 50% writes, then the boost is bigger than with only reads. Now, this is because hard drive disks are better at handling reads than writes, so the solid state drive cache has a benefit, but it's not as big. So, what does benefit from SSD caching? Well, for start, all file and block storage services see a benefit. So file storage being data stored as a single piece of information inside a folder, for instance BTRFS, and block storage using iSCSI. Virtualization also benefits from using an SSD cache, as this reduces storage I/O latency and results in the consumption of less CPU and memory resources on the host. So less congestion of the CPU with queued storage I/O requests means more computational resources are now available, so more VMs can be configured on the server. OLTP, or online transaction processing, or anything with the database perhaps, also benefits, as well as instances where you have some sort of data access pattern. But what scenarios don't benefit from SSD caching? So, any large sequential reads and writes, like HD video streaming or surveillance video recording, as well as entirely random access, so if there's no pattern at all, and so it lacks rereading patterns, then that doesn't benefit from SSD caching. So an SSD cache can be used in a variety of scenarios, so some use cases where the use of SSDs and caching could be a business file server document library. So a read cache would be of benefit here, as a fast access to multiple documents, as well as the data is not changing, so write operations are not necessary. So you can think of this as a place where legal and compliance documents might reside in. So for example, it could be used for reference when working on a project. So if there's no write operations applied to them, then this would be a great case for a cache. Now, Synology high availability can also benefit from a read-write cache, as both caches have to be identical in the high availability environment. And a read-write cache can help with heartbeat and syncing operations, as well as increased performance of the syncing features. And finally, anything with a database, so a mail server can benefit from a read-write cache. Mail servers in particular deal with a lot of reread operations, so read caching and the read-write cache helps with those operations. And incidentally, Synology cache itself has been developed with databases and R units in mind. But with very large user cases with lots of loading, a full volume might be a better solution, so I'm going to talk about that later on. Now, sometimes an SSD cache may not suit your needs, so instead you're going to need to look at an all-flash array, where flash is just another term for SSD. So these are solid-state storage disk systems that contain all SSDs instead of either hard drive disks or a mix of the two in a hybrid system, like an SSD cache. Now first, I'm going to go over all-flash arrays, and I'm going to talk about how they can help, and then I'm going to go over the Synology SSD range and the new additions we have that can benefit your business. So, all-flash arrays are mostly used for transactional and extremely high throughput applications where speed and time are of the essence. So, things like financial trades or very large e-commerce websites, or, as mentioned previously, email servers, where you're trolling through lots of files for specific data. As I mentioned earlier, SSDs require less energy to function, so all-flash arrays consume less in terms of energy, as well as the running costs are therefore smaller, as well as the units themselves, so they can save in terms of storage overhead, for instance if they're deployed on a server farm. What all-flash arrays do is offer pure performance where you have multiple gigabytes per second of random data throughput or very high I/O operations per second, whereas a cache needs a pattern in order to be effective. As I said, email servers with a large number are a great example where SSD caching might not be sufficient. Hosting on a hard drive disk with a cache may be possible, but anytime an operation involves cold data, the users will have a bad experience. So what type of operations can happen? Well, if you search for an email that was archived over a year ago, a search like this will take a long time to return, as the system will need to perform it on a slower hard drive disk volume. And with multiple users, this can cause a bottleneck. So now we have some general tips to enhance performance in a deployment. So the first is relating to creating volumes. The recommendation is not to have a single iSCSI LUN or shared folder in a single volume, but instead for performance, to have at least 2 volumes, preferably more, and in each volume to have 2 shared folders or 2 iSCSI LUNs. As an example, things like VMs, if you have a lot of those, then they get the maximum amount of IOPS if you have multiple volumes and multiple LUNs on each volume. So here I want to focus on the LUNs. So the recommendation is to create 2 LUNs per volume. So over 2 volumes you'll have 4 LUNs, and this can help alleviate bottlenecking. And here it's more thick provisioning over thin provisioning, so allocating the capacity of the LUN from the offset and doing older calculations at the front end. Now on shared folders, don't enable data checksum as this is disabled by default. Depending on the protocols you may use, you might find some performance enhancement by disabling the server message block or SMB encryption mode, and then to set the network file system read and write package size to 32 gigabits per second. Now, both of these are found in the advanced settings. Additionally, you can set the iSCSI queue depth to 128, and with regards to the queue depth, the longer the queue depth, you'll generally have better performance. However, it's really not advisable to change this unless you're recommended by the vendor. So in this slide, we're going to focus on VMware again, and here we can see the recommendation is to set the queue depth to 128. As because the queue is longer, we can bring in more I/O. However, you might impact the latency here if you haven't filled the queue, as it might not get flushed. On all flash storage where you have old SSDs, you should absolutely set the queue depth to 128. However, with hard drive disks, this may cause fluctuating latency as it flushes more data at one time, and this is why the default is not set at 128. So this is a trade-off and a choice to be made. The default I/O queue depth is 16, so we can choose thick provision eager zeroed, which is a VMware provision format, and this will create a VM disk in a default thick format, so the space required for the virtual disk files is reserved when the VM is created. Now, don't forget to disable ATS heartbeat and delayed ACK. So now I'm going to talk about network thresholds. So here you can see 2 networks. We have a 1 gig network and a 10 gig network, and we can see their throughput and the theoretical maximum IOPS. For the 1 gig, it's just over 30,000, but for the 10 gig, it's just over 300,000. So a common problem here is that this is mainly overlooked, and you must make sure your network matches the speed of your Synology. So here we can see 4 regular hard drive disks, like Western Digital Reds, in a RAID 5, and you can see the IOPS is at 272. Now we can see that this exceeds the network threshold of 125 megabits per second at 417 megabits per second. So to overcome this, we don't need to upgrade to a 10 gig network, as we can use link aggregation or bonding to overcome this. Now in the next example here, we can see 4 SATA SSDs, which means the IOPS has significantly increased. You can see here that the amount of IOPS is greater than the maximum for the 1 gig network, almost 3-fold. And then for the 4 SAS SSDs, where the IOPS even supersedes the 10 gig network, link aggregation can help here. So in terms of different cache array types and all-flash array types, a read-only cache can be created with up to 12 SSDs and can be configured in either a basic or RAID 0 configuration. As I said earlier, this is used for things like document stores, where you are simply reading the files. The read-write cache can be mounted in either RAID 1, as I demonstrated earlier, RAID 5 or 6, and again can use up to 12 SSDs in the array, and this helps speed up database queries. And finally, RAID F1. So this is a proprietary RAID type developed by Synology. It's a derivative of RAID 5 and causes an uneven parity distribution. So one SSD will reach the end of its lifespan before the others, allowing you to swap this out with no downtime and avoid older disks reaching the end of their lifespan at the same time. So there are a couple of other things to bear in mind when selecting SSDs, and I think we've covered the majority, but just to be sure, here are some last tips before we move on to our new products. So here we can see in these graphs, they represent IOPS performance, and the consumer drives look amazing at the front end in terms of performance, peaking at 140,000 IOPS, whereas the enterprise grade drive peaks at just over 40,000. However, you can see that the consumer grade drive is inconsistent and the distance between the peaks and the troughs are very wide. So one of the most crucial aspects when selecting disk drives is of course the difference between enterprise and consumer grade disks. So here I want to introduce to you some terms that you may or may not be familiar with, then elaborate on these so we can understand what we're looking at when we select disks for your implementation. We're going to speak about open provisioning later on, and just to let you know, this is going to be about garbage collection and wear leveling, and typically an SSD will be 7% over provisioned. Now this is a portion of the space on the SSD that is used by the disk controller firmware, and you'll find this on enterprise grade disks. In addition, enterprise grade disks tend to include PLP or power loss protection in the form of an onboard capacitor. Now this does two things. If there's a power loss, it safely flushes the in-flight data to the persistent or non-volatile memory and maintains the integrity of the SSD mapping table so that the SSD is recognized and usable again upon reboot. Lastly, the TBW DWPD, or terabytes written and drive writes per day. It's common to see these two terms used in spec sheets to determine the endurance of the drive. And both these approaches are based on the manufacturer's warranty period for the drive. So now I'm going to talk to you about some new products that have entered the Synology range. Now these were added on the 11th of June and are available right now. These products are all solid state drives, and these are an important milestone in the Synology revolution. And the first question is, why are we entering this market? Well, there are a number of compelling reasons. Primarily, they allow customers to benefit from a one-stop shop solution for a fully integrated all-flash deployment, with the knowledge that both the unit and the disks are supported by Synology's wealth of experience in the marketplace. We're not looking to become an SSD brand as such. What we aim to do is enhance our platform and deliver better value and customer experience to the Synology community. So, how do we plan to do that? Well, we have a few key factors that we feel are important attributes to any SSD that you're liable to use in your Synology unit, whether that's in an SSD cache or an all-flash array. So, enterprise-grade performance. We want to ensure that enterprise customers can get the best possible and stable performance in our system. So here, you can see there's a name brand SSD, and this is quite large peaks and troughs and quite low in the IOPS to be honest. But the Synology SAT 5200 has a consistent IOPS at 70,000. So we deliver consistent throughput over time, and we provide 1.3 drive writes per day within the 5-year warranty period to withstand 24/7 intensive workloads. Now, we're compatible, fully tested and integrated into the DSM, so there's no need to wade your way through the compatibility list to determine if you have the right disks for your unit. These disks have proven interoperability with Synology systems through a rigorous validation process, so if there's a firmware change, as these are all under the Synology umbrella, they're always going to be compatible. So, how do we achieve this? Well, later on, we're going to speak about different technology within SSDs to make this work at the enterprise level. We have wear leveling, garbage collection, and triple level cells to offer the capacity we require. So this is one of our products. It's a 2.5-inch SATA drive, and it's available in 3 capacities. There's 480, 960 gigabytes, and 1.92 terabytes. So these are enterprise grade disks supporting 1.3 drive writes per day, and they have power loss prevention integrated via an onboard capacitor. They can handle 70,000 sustained 4K random IOPS for the consistency needed and a maximum latency of 15 milliseconds in testing. So here we have a few enterprise grade SSDs from our other competitors, and you can see that there's some peaks and troughs here, and consistency is missing within our testing. But here is our Synology unit, so it's a Synology SAT 5200, and you can see here what the performance of these new Synology disks look like. So in this Synology unit, you can see that we deliver a much higher IOPS on a much more consistent performance. So circling back to my earlier point, this allows you to predict the speed and spec out your solution accordingly with a consistent experience needed in the enterprise environment. So here you can see the Synology SSD at different stages in its lifespan. You The blue line indicates a brand new disk, and the red line indicates a disk with only 24% of its lifespan remaining. As you can see that although the IOPS decreases over time, the performance is still consistent even as it approaches the end of its lifespan. So just to touch on one of the big advantages of Synology branded SSDs, be them 2.5-inch SATAs or our new enterprise grade M.2 NVMe's, because they're fully integrated into the DSM, we can proactively manage the lifespan of the disk with the lifespan analysis tools available in the DSM. So whilst the SAT 5200 range is ideal for large pools of fast storage, we also have the S&V range, which are M.2, and they're designed for customers needing to set up a cache, so they optimize performance at the lowest possible cost. So these are the S&V 3400 and the S&V 3500. Both of these are enterprise grade drives designed and built specifically for SSD caching. Now they have an endurance of 0.7 drive writes per day and are both 400 gigabytes in capacity. The S&V 3400 is an M.2 2280. So this is in the M.2 form factor and is 22mm wide and 18mm in length. However, the other SSD, the M.2 22110, is again 22mm wide, but it is 110mm in length. Both of these sustains 40,000 4K random IOPS with a latency of sub 35 milliseconds in testing. Now, the important thing to note here is that these are both enterprise grade M.2 NVMe disks. So the most competitive products in the marketplace so far are either consumer grade or not designed for caching, and usually boot functions instead. Whether our products change that. So all three of our products are backed up by an exclusive 5-year warranty and are integrated into the Disk Station Manager for firmware updates and lifespan analysis for sudden failure avoidance via proactive disk management. So just to give you an overview of our naming convention, I've run through this with the SAT 5200 480GB. So the first letter is S, and this is the drive type. So S for SSD, as we know all these drives are SSDs. The next two are the interface, so AT for SATA, NV for NVMe. Then we have class 3 for enterprise value, 5 for enterprise standard, and 7 for enterprise premium. Next is the form factors, 2 for 2.5 inch, 3 3.5 inch, and 4 and 5 for M.2 variants. Generation is the next one, so 00 for first, 10 second, and so on. And finally it's capacity, so 480, 480 gigabytes. So that was Synology SSDs, and now we're in the final part of our agenda, which is technology. So I'll talk about choices, benefits, and drawbacks of SSDs and hard drive disks. So what benefits do hard drive disks bring? Well, capacity is one. So at present there are opportunities to purchase large capacity hard drive disks in the marketplace. Cost is another. So for now, hard drive disks are cheaper per terabyte, with hard drive disks approximately £25 per terabyte, but solid state drives are about £100 to £250 per terabyte, depending on the grade. And finally, supply. So they're easy to replace as there's multiple channels to purchase hard drive disks. So supply is not an issue. But what benefits do SSDs bring? Well, they're faster, so there's no moving parts, so high performance, which means faster load times and faster read-write operations. They're also quieter, so this might be a consideration for you. We have customers who work in sound-sensitive environments like recording studios where noise is a factor, so these solid-state drives are perfect. And finally, they consume less energy, so this might be attractive if you have a green initiative. And they're cooler, so this reduces thermal stress on the machinery. Less moving parts also means they have less opportunity to wear down. And I'm going to cover how this is achieved on further in the section. So what performance do you need? Well, this is at the heart of decisions that you make regarding not only this choice, but how you deploy them to get the best configuration for your workload. So the number of different terms are thrown about when discussing disks and performance, and three are key here. They are throughput, IOPS, and latency. So to take a real-world analogy, throughput, if you can imagine, is if you're on an autobahn in Germany and you're getting the maximum speed your car can travel down the road and reach its destination. Now, this is the same concept for throughput, as this metric measures when the maximum speed data can successfully move through your system from one place to another. Now, the acceleration and handling of the car, much like a car travelling through a scenic road or the tight turns in Formula 1, is where maximum speed isn't a key factor, and this maps out more directly to IOPS and latency. So, how do we optimize this? Well, the best way to think of this is if you imagine you and 20 other cars arrive at a toll road, but only one booth is open. So the booths in this analogy are the hard drives and the cars are the I/O. As you can imagine, a big queue will form, and this is referred to as the queue depth. So to optimize latency and increase the amount of I/O, you should increase the amount of toll booths open, which in turn means increased amount of hard drive disks or solid state drives. Now, disk latency refers to the time delay between a request for data and the return of the data, and is critical to performance of the system. SSDs can deliver very low levels of latency at around 13 milliseconds. So, low latency is great, as the traffic is flowing and requests and responses are getting to and from the destination quickly. In terms of IOPS, 4 primary factors can affect this. So first, it's multi-disk arrays, as more disks in an array means a greater IOPS, as if one disk can perform at 150 IOPS, then 2 can perform at double that, so 300. Now, next is the average IOPS per drive. So the greater the number of IOPS each drive can handle, then the greater the total IOPS capacity. Now, this is largely determined by the rotational speed of the drive. Next is RAID. So the application is likely using a RAID configuration for storage. So this means that using multiple disks for reliability and redundancy. Some RAID configurations have a significant penalty for write operations. So for RAID 6, every write request requires 6 disk operations, but for RAID 1 and RAID 10, a write request only requires 2 disk operations. So the lower the number of disk operations, the higher the IOPS capacity. We'll talk about RAID a little bit later in the webinar. So to recap, throughput is the actual rate of speed data is traveling through your network. IOPS is the input and output operations per second. Latency is the time it takes for that I/O operation to complete. And then I'm going to add a further metric here, which is I/O size or block size. And it's important for us to know how to work this out to see how efficient the other 3 concepts are. Now, this is usually measured in kilobits. So, how do you calculate the throughput? Well, it's a relatively simple formula. So, we take the amount of IOPS and we multiply this by the I/O or block size. So you can see in this example here, through 1000 IOPS times by 4 kilobits is equal to 4000 kilobits or 0.5 megabits per second. But how do you figure out the IOPS and calculate it? Well, it's 1 being a disk divided by the sum of the average latency and average seek time. So you can see here that the I/O size or block size is an important factor in the formula. SSDs are limited as they can't override data, so this means that the more they fill up, then there's less performance. Now, to compensate for this and to increase the lifespan of the SSDs, the manufacturers over-provision. So a key way of doing this is with garbage collection and trim, and these operations are found mainly in enterprise-grade SSDs. Now, the goal of garbage collection is to keep as many empty blocks as possible. So when the SSD needs to write data, it can. So it's clearing out invalid pages of data. The SSD controller then reads all the good pages of a block and writes them to a newly erased block. In this diagram here, the trim command has been triggered, and I'll show you how to enable that shortly in a demo. Now, this alerts the SSD controller that garbage collection needs to take place. As you can see in illustration 1 here, both block A and block B have invalid pages, which you can see in the grayed out areas. The blue areas from A to H contain valid information, and the SSD controller is alerted by the trim command, which recognizes the valid data and transfers this to block C, which is seen in figure 2 here. After this job is done, the system can erase block A and block B, as seen in figure 3, and now new data can be written to the freed up blocks of A and B. So, trim is the command that kicks the process off, and garbage collection is the operation of relocating existing valid data to another block, allowing the block of invalid data to be erased and new data to be written to it. You might be wondering why garbage collection and trim is needed. Well, trim makes sure to reduce the amount of erase cycles, which enables the drive to last longer. By avoiding unnecessary copying of invalid data, the write operation of the drive will speed up. So now I'm going to give you a demo on how to set up trim, and I'm going to show you how to set up a schedule for trim. So this is useful to do to make sure there's minimal disruption to the office. So here, we're going to click on the main menu, and again click Storage Manager. I'm going to click Volume on the left, and then Action and Configure. So I'm going to click on SSD trim at the top here, and then we're going to enable trim. So once we're in there, we can click Set Schedule, and this will allow us to set schedule either daily, on certain days, and set time as well. So click Enable here and set the schedule. So as I mentioned, you can set it for daily, weekends, or weekdays. Now this is useful to do to make sure that no one's in the office, so there's minimal disruption. So we're going to do this by setting it to 1 AM and click OK. And OK again. And that's it. So now I'm going to talk about wear leveling. So SSDs, blocks, and cells can only be written to a certain number of times. So it's therefore essential to even out the workload on those cells. Now wear leveling works by using a control in the SSD to make an erase count of each block and then subsequently writing data to the block with the lowest erase count. So this evens out the write operations across the block and extends the lifespan by evenly distributing the workload. So you can see there in the top one, the device without wear leveling, everything was getting to the top 2 rows and it's leading to a few cells dying off. But with wear leveling, everything's all spread out evenly, so the SSD can last longer. Now I'm going to go over another aspect of SSDs, and it's the terms SLC, MLC, and TLC. So these refer to the structure of flash memory cells and how many bits each cell can store. SLC is single level cell, stores 1 bit. MLC is multi-level cell and stores 2 bits. And TLC is triple level cell and stores 3 bits. Because MLC or TLC can store more bits, they have a larger capacity, but the trade-off is usually shorter lifespan for the disks. Now, by and large, MLC and TLC disks have mainly been offered as consumer-grade disks. However, we'll see later on that this is an area that Synology have worked hard at, and we've implemented features to introduce new TLC disks that you've seen earlier that offer the capacity and endurance at an enterprise level. So now I'm going to show you how the lifespan and storage capacity is affected and applications for each of these. So SLC is the longest lifespan and charge cycles, and it's used for industrial use, so workloads that require heavy read and write cycles such as servers. MLC has a low production cost that is usually passed on to the consumer, and it's for everyday consumer use, so gamers and enthusiasts, but it's more specialist. And TLC is finally large storage capacities, and it's for everyday consumer use, so web and email machines, netbooks, and tablets. So now I'm going to give you a quick overview of M.2, NVMe, and SATA. Now M.2 and NVMe might seem like interchangeable terms, however, there are big differences, so I want to clarify these before we move on. Firstly, M.2 describes the form factor, so you can think of M.2 as a stick of chewing gum in terms of shape. There are different sizes, so here the first 2 digits are the width in millimeters, and the second set of digits represent the length. The most popular form factor right now is 2280. Now M.2s can be either SATA or NVMe versions. SATA, as some of you are aware, is the interface that connects the host bus adapter to the storage device and has been a standard interface for hard drive disks and SSDs for almost 2 decades with a number of revisions. NVMe, or Non-Volatile Memory Express, is a communication standard developed especially for SSDs. Now this allows drives to act more like fast memory than hard drive disks. NVMe drives can also fit into the PCI Express slot on the motherboard, so much like a graphics card. And they typically come in the M.2 form factor. You can see here in the bottom graphic that NVMe is more than 6 times as fast as a standard SATA 3 connection. So these are ideal for the ever-evolving demands of the modern enterprise, where speed is of essence. Now I'm going to look at some real-world scenarios with you, where hard drive disks and SSDs are important, and how you can gauge at what sort of scenarios they should be selected in. So here we have a hard drive disk versus solid state drive test. And we tested a single user uploading a large file to SSDs and then to an array of hard drive disks. We often get inquiries from single users such as photographers who want an old SSD system, thinking that this is going to be super fast and quick to access and use. So, you think an SSD means faster speeds, right? But that's not necessarily true. As here with a single user uploading, SSDs don't make much sense. In fact, the Iron Wolf 240GB disks only registered 230 megabits per second. So we can see here that it's not a straight question of an SSD being faster, as a larger array of hard drive disks may outperform the solid state drives. So, as you have more hard drive disks to write to at the same time, these can result in an uptick of an overall transfer speed. So, this means that because of the array, it can be written to faster and can beat out the SSD. However, if the team had 10 photographers uploading data, then the patterns would be much more random and the SSD would handle that better. So whilst the hard drive disk with their moving parts would struggle to keep up with performance. So here, as we talked about SSDs themselves, a useful piece of information which is useful to increase their efficiency is maximum transmission unit and jumbo frames. So if you have a fast link, so a 10 gig network, and you want to increase the efficiency, you can increase the maximum transmission unit of the packets that can be sent along your network and decrease the amount of packet headers and process overhead. So the standard Ethernet MTU size is 1,500 bytes, and this is usually the maximum transmission unit. However, by introducing jumbo frames, you can increase the size to 9,000 bytes. Now, this is only really useful if you have a fast network. And with jumbo frames, just note that routers and switches often get bogged down, fragmented packets of different sizes. As if one device wants a 1,500 byte payload, but you're sending 9,000 bytes, the packet will either get dropped or broken down into several smaller packets, and this can cause strain on the device's CPU. In an analogy, with standard frames, it's like you're moving house, and you have to take multiple trips in the car to get all your stuff to the destination. But with jumbo frames enabled, you have access to a huge moving van that can take all your stuff in one trip. I'm going to show you a case study now of the media bunker, and this shows the difference that adding jumbo frames can achieve, and then I'm going to show you how to enable them. So the Media Bunker are a video production company based in Fareham in Hampshire, and they use DS3617XS for the Seagate Exos drives in a RAID 6 configuration. Now, they chose to use a hard drive disk array as this is sufficient for their workload, and they have a small team, so rarely more than 2 clients will perform data writes simultaneously. Now, before jumbo frames, they had a read speed of 1,445 megabits per second and a write speed of 1,695 megabits per second. But once they've been enabled from the NAS to computer, they allow doubling the read speeds and boosting the write speeds. So you can see that even without SSDs, jumbo frames can improve the overall speed. This speed boost is due to not much randomness and sequential transfers using jumbo frames. Furthermore, the large number of drives in the array has managed to let the storage match the throughput of the dual 10 gigabit card. However, with large teams, data patterns could be more random and will require SSDs. So how do we do this? Well, first we need to enable jumbo frames in the DSM on the NAS. We can do that in the control panel under network and select network interface. This does have to be done for an interface, so LAN port, 10 gig one usually. Then we need to enable it on other parts of the setup. So in computers, it's Windows. It can be done device manager for each network adapter, and in the rest of the network, any pieces of equipment need to be enabled. If any part of the setup doesn't have this enabled, then the jumbo frames will just fragment. So that was technology, and that was the agenda. So we've gone over SSD caching, if it's right for you, and how it can impact your workloads, Synology SSDs, and all-flash arrays, and the new additions to the Synology range and why we've decided to enter the marketplace. And then, finally, we've gone over technology just now. So we've gone over the choices, benefits, and drawbacks between your solutions, whether using SSDs, hard drive disks, a hybrid solution. So that was the webinar, and I hope you enjoyed it, and I hope to see you in the next one. Thank you.